opportunity to talk about the immense potential that digital twins bring to the renewable industry, particularly the solar industry. This is perhaps an odd image to start a talk at a renewable energy conference. When people ask me what my first impression of India was, my answer is that I was very impressed that despite the exceptional volumes of traffic, certainly by Canadian standards, the traffic keeps moving and largely without collisions. And the question is why? So we'll get back to that later. This is actually a talk about digital twins. So let's start with what they are. All of us, I think, are familiar with the traditional physics and engineering principles-based models, expressed typically as mathematical equations and implemented in software. These models are developed by highly skilled domain experts, but the models that result represent an idealized component, and the key limitation is that it's a static model. It's developed ahead of its use. Right? A digital twin or AI model, more correctly, a machine learning model, is developed from data collected from sensors themselves. Domain experts help in terms of what data should be collected, but effectively the machine trains itself. The advantage of digital twins is that it can merge the average performance of similar units with the individual performance of the specific unit that is being modeled. And in particular, it can adapt to changes in performance over its lifetime. To summarize, the advantages of a digital twin are that it takes into account the average and the variance in performance of peer units. It more accurately models the individual tolerances, the history, and the damage experienced by a specific unit, and it automatically modifies itself to account for changes in the environment, degradations, and in aging. So to help understand how digital twins help the solar industry, let's focus for a moment on the challenges the industry faces. While the order of the importance depends on the individual producers, these are broadly, but there is a need to optimize the yield and to control operations and maintenance costs as PPA prices fall. As the proportion of energy produced by solar increases, the demand by the grid operators also increase, resulting in regulatory penalties. Plant sizes are growing, and with that, we need to focus on the problem areas of the plant, not the normally operating areas of the plant. A previous speaker commented about geographic distribution. The larger operators are tending to run 10, 20, sometimes even 50 plus plants. And there's a need to monitor and to some extent control those plants remotely. And finally, plant behavior changes substantially as the plant ages. Something like light-induced degradation is not an issue when the plant is 2 years old. When the plant is 15 years old, then it becomes a concern. This, on the other hand, is good news, right? These challenges are challenges of a successful and growing industry. The even better news is that digital twins help with almost all of these problems. So the two key strengths of digital twins are that they have the ability to identify anomalies and that they have the ability to predict short-term behavior. This translates into the ability to focus maintenance and the ability to schedule preventative maintenance. On the regulatory penalties side, the ability of digital twins to accurately predict the yield of a plant enables producers to avoid those regulatory penalties. As plant sizes grow, the deviation in performance should not increase in panels from a reputable manufacturer, but the actual number of panels with substantial deviation from the mean performance does increase. Right? The capability of leading-edge machine learning models is actually their ability to distinguish normally occurring outliers, a panel that runs slightly hotter than others or generates slightly less power when it's a cloudy day. From panels where a failure event, like a crack or a burnt out cell, has actually occurred. Additionally, addressing the geographic distribution, digital twins naturally adapt to their operating environment, but their output is actually data. So we can create centralized data lakes, allowing us to do remote monitoring and to create remote control systems. And finally, possibly the biggest strength of a digital twin is in its ability to adapt to emulate the changing performance of a unit as the plant ages. Where does this power actually come from? The real reason is that a digital twin can model in 3 dimensions. There's the familiar time dimension, where the model uses past behavior to predict future behavior. This gives the producer yield prediction, failure prediction, and failure pattern identification, giving advanced warnings. But the digital twin also has the ability to learn from the behavior of its peers. And this provides the ability to distinguish anomalous performance from natural variance in behaviors. It also provides the ability to model changes in the average behavior itself, in other words, to handle the aging of the plant itself. And finally, there's the contextual axis. This is geographic location or position in the plant hierarchy. This enables a digital twin-based monitoring system to identify or locate specific problems, to conduct internal consistency checks, and to provide directed O&M, which areas of plants are currently experiencing problems and would most benefit from intervention. Since we're running out of time on the talk, I'm simply going to mention some other areas where digital twins have potential to provide value. The predictive capability of digital twins allows the creation of as-needed scheduling, for example, for panel cleaning. The ability of certain machine learning models to learn both long-term and short-term behavior allows for models accounting for seasonal variations. Using digital twins at different levels of the plant hierarchy enables error triangulation. Did the panel degrade, or is it the fact that the sensor has become uncalibrated? In the longer term, using digital twins with weather data allows us to learn patterns that predict catastrophic events like hailstorms. And there's always the capability of adapting to changes in the plant structure itself. So back to our traffic image. The reason the traffic seemed to work was that there was a local processing engine, the driver, right? The awareness of the capability of the individual vehicle and awareness of what the peer entities were doing through the sound of the horns behind them. This led to the driver making sensible decisions individually within the overall context of the system itself. And this is perhaps the idea of a self-aware system. Digital twins take time and compute power to train, but once trained, their operation is very efficient and requires very little processing power. So as we look into the future, as sensors and some of the processing power moves to the edges, closer to the panels themselves, the digital twin models can move with them. Perhaps the greatest opportunity represented by a digital twin-based system is in each component of the plant adapting to optimize individual capacity while taking into account the requirements of the system as a whole. Hopefully, I've provided some justification for the inclusion of digital twins in the solar industry, and I'm looking forward to exploring digitization further in the upcoming panel discussion. Thank you.